Hello friends, I welcome you all in my series of lectures on generation of microwave signal. This is my seventh lecture and here we are studying about low power microwave generators. Up to six lectures we have seen high power microwave generators, that is the tubes. Now here we are going for low power microwave generators, that is the diodes and transistors. So these diodes and transistors are having advantage like they are low, they will generate a low power at a very high frequency, that is in a microwave range. Similarly, they are very compact and they are very cheap. As they are compact and cheap, they are useful in all experimental purposes, or they can use in the practical applications also, like satellite communications and all. Now, the first, and these devices are also called as solid state devices. Now, see, the first diode that we are going to see, that is a gun diode. It was invented by the scientist Gun. So the name is given as a gun diode. If you see the construction of this diode, it will have all n plus layers. That is, middle layer is active n layer. Then surrounding to active n layer, on the top and bottom there is an n plus layer, and below that or above that there is a metallic contact layer or a metallic contact. Now if you see, there is no PN junction in this structure. As there is no PN junction, then how it is acting as an diode? You can see is as there are a N-type, generally the component which is used, that is the gallium arsenide. If you have an active layer of a gallium arsenide of a 10 micrometer, then it will give the output frequency equal to 10 gigahertz. Now it is surrounded by N plus layers. Now if you are connecting this N plus layers to the supply, if you whatever the N plus layer we are connecting with a positive supply, that will act as an anode, and whatever the N plus layer that will connect to a negative supply, that will act as a cathode. Now if you are connecting it to the supply, positive and negative supply, the device will act as an anode and a cathode. Now this will act as it is acting as an anode and cathode, it is called as a diode. So this device is called as a gun diode, though it don't have any PN junction. Now, how this device then work, or how the current is outputted in this device. Now, generally all the substrates are having two energy bands like valence band and a conduction band. Now, in this device, as we are having many layer of N-type, N plus type materials, then or N-type material, then in a conduction band, there are many energy levels. These energy level we can call it as in a lower valleys and the upper valleys. Now, if you give a supply voltage V to the device, then the electrons which are present in a valence band, they will absorb the energy from the supply and their energy goes on increasing. As their energy goes on increasing, they will jump to the conduction band. Now, as they are jumping to the conduction band, their mobility goes on increasing. And mobility is directly proportional to conductivity, and the conductivity is directly proportional to current. So, the output current goes on increasing. Output current goes on increasing. Now, as we increase the supply voltage, many number of electrons from the valence band will absorb the energy and jump to the conduction band. As more and more voltage is increased, more and more electrons will jump to the conduction band. Then from lower value to upper value, like that they will start jumping. But as the more number of electrons are there in a conduction band and they are coming again in a conduction band, then the large number of electrons which are there in a conduction band, they will start to form the group, or they will start to form the bunch. As the group or bunch is formed, you know that the mobility goes on decreasing. Now, as the mobility goes on decreasing, the conductivity decreases. And as the conductivity decreases, output current decreases. So the device start giving decrease in a current. If you plot the current or voltage characteristics for this device, it will look like this. Initially, if we are increasing the voltage, current goes on increasing, and if we keep on increasing the voltage due to the forming of the bunch of the electrons, the current goes on decreasing. That is, this decrease in a current, that is called as negative differential resistance region or negative resistance region, that is generally used in the oscillator. So this device can be used as an oscillator, and this can be used as a microwave signal generator. When we are using this device as a microwave signal generator, or when we are operating the device in such a manner, then the large amount of heat is generated in the device. Now to dissipate this heat along with the metallic contact, there must be always heat sink. So if you see the structure of device, that will become n-type buffer. Then buffer is surrounded by N plus gallium arsenide substrate, and then the metallic anode and cathode along with a heat sink. The structure of a device. If you see an equivalent circuit of this device, that will representing the junction resistance capacitance, then the lead resistance capacitance and the series resistance. And this device will operate depending upon either we are connecting this device as an individual one, or either we are connecting this device along with the external tuning circuit, LC circuit. So depending upon that, there are various modes of operation. There are two principal modes. One is called as transit time mode and another one is called as limited phase charge mode. Then along with these two principal modes, there are two special modes are also there. One is called as Ponch domain mode and another one is called as delayed domain mode. Now this Ponch domain mode or delayed domain mode, these are special modes. So we will see one by one all these modes. First it is in a transit time mode. So as it is a transit time mode, then we can see here, it is the first mode of operation. We can see here the the device is connected in between the positive and negative supply. So that will have a cathode at one end, anode at another end. Now, as we go on increasing the supply, then what happens near the cathode? The bunch of electrons is formed. And this bunch of electrons, which is having a slow mobility or less mobility, it will, as this is the electrons, that is negative charge particles, they will try to move towards the anode. So as the mobility of this bunch is decreased, it will take some time to move towards the anode or reach to the anode, and the time taken by this bunch of electrons from cathode to anode, that is called as transit time. That is called as transit time. So when the bunch of electron is near to cathode, there is no output current at an anode. There is no output current at an anode. Now when this bunch of electron travels towards the anode or reaches to the anode after the transit time, at an anode, suddenly the large amount of electrons are reaching. So at an anode, large amount of current will be there at an output side. Suddenly there is a increase in a current at an output side because this domain breaks down. So whatever the bunch created near the cathode bunch of electron is called as domain, and some voltage is dropped across this domain, so there is no signal, no current at an anode. So suddenly this domain breaks down, suddenly current increases at an anode. Then again the second domain is started at an cathode. When the first domain reaches to the anode, second domain is started at an cathode. And that second domain also takes some time, that is equal to the transit time to reach to the anode. By the time the first domain has already finished out its operation and there is no current at an anode, that is zero current at an anode till the second domain reaches to the anode. When the second domain reaches to the anode, then again there is a very large current present at an anode. So if you see the operation of a device, then there will be the very large current for a small time. Then there is a zero current. Then again the large current when the second domain reaches. Then again the zero current by the time the third domain reaches, there is again large current. Now if you plot the signal on a timeline axis, it will look like a pulse type of signal. It will look like a pulse type of signal. So we can say that this gun diode generates a pulse, a current pulse at a microwave frequencies. And this is a transit time domain mode. This is a transit time domain mode. It is called as transit time domain mode because the time taken or the time difference in between the two pulses is equal to the transit time, and that is equal to the time taken by a domain to travel from cathode to anode. Now we will move to the next domain or next mode of operation. Here the gun diode is connected along with the external LC circuit. As the gun diode is connected along with the external LC circuit, then the external LC circuit, resonating frequency of this external LC circuit is very very large as compared to the frequency of an transit time frequency of an gun diode. So, as the frequency is very large or resonating frequency is very large, then there is not a sufficient time given to form the domain. The formation of a domain has not been done. Formation of a domain has not been done. Not a sufficient time to give time is given to form the domain inside the device. So whatever the current, that current is moving towards the anode, and it is always in the negative. Device is always kept in the negative resistance region. So finally we can use it as an oscillator, and we can form an output current. Continuously we are getting here an output current as shown in this VI characteristic diagram. We can see some specification regarding this LSA mode, why we are getting an oscillations over here. That is, here resonant frequency is very very greater than transit time mode frequency. Applied DC voltage is greater than the threshold voltage. That is, device is operated in a negative resistance region. So RL is greater than or equal to 1.2 Rg, and for steady state oscillation RL must be equal to Rg, minimum requirement. Now we will move to the third mode, that is a Ponch domain mode. In the Ponch domain mode, the gun diode is connected with an external LC resonating circuit. Then the tuning frequency of this external resonating circuit is slightly greater than the transit time frequency. So domain is allowed to form. Domain is allowed to form. But a sufficient time is not given for a domain to reach to the anode. So what happens? The domain is broke down in between, or domain is conched in between. That is called as conching of the domain. The domain is conched in between before it arrives to the anode due to the onset of the negative swing of oscillations. Or we can say that as the sufficient time is not given, it is not able to reach to the anode, it is get conched. And we can, in technical words, we can say that dipole domain is conched before it arrives at the anode due to the onset of the negative swing of the oscillation. Otherwise, whatever the thing in this domain or in this mode of operation, it is similar to the transit time mode only. So we can have a current outputs. Then then the fourth type of mode, that is the delayed domain mode. In the delayed domain mode, the resonant frequency is kept small as compared to the transit time frequency. Then then the domain is allowed to form. The domain is also called as dipole domain because as a bunch of electrons are there, then the voltage will get dropped across it. One side of that bunch is having a negative charge, and another side is having a positive charge. That is, cathode side is a negative charge, anode side is in a positive charge. So it can able to travel. So it is called as dipole domain. So dipole domain or a domain is allowed to form, and it is allowed to travel. It has given it a sufficient time to reach to the anode. It will reach to anode also. But resonant circuit is having the frequency less than the transit time frequency. So domain has to wait on the anode. Domain has to wait on the anode. That is, once the domain is formed, it will reach to the anode, it will give the output current, but immediately second domain will not get started as the transit timer. Here, the second domain formation is delayed because of this resonance circuit. Immediately when the first domain reaches to anode, second domain is not started. Second domain is started after some time. So it is called as delayed mode. It is delayed due to this LC resonant circuit frequency, which is less than the transit time mode frequency. So we can write like that, but the formation of new dipole is delayed until the oscillation voltage increases above threshold voltage. So mode will be delayed. So this mode is delayed and it is called as delayed. So if you see in a practical gun diode, it will have some tuning curves, it will have some DC bias arrangement, and it is having a shortening piston. So we can adjust the operating or the output frequency as well as various domains to the device, various modes of operation for the device. Okay, this is about an gun oscillator. Then the continuous power output, it is in a few watts. Then the pulse power output is 100 to 200 watts. Bias voltage required is 10 volts. Bias current is 1 ampere. Then the frequency it can output that is equal to 8 to 40 gigahertz. Frequency tuning range is 2%. Output power is limited by the heat dissipation as I told you. We always use a heat sink with the device. Then small size, advantages are small size, ruggedness and low cost. Now we will move to the another diode, that is the avalanche transit time devices or avalanche transit time diodes. Now what is the avalanche transit time diodes? That will work upon or operate upon an avalanche effect, avalanche breakdown effect. So this is called as avalanche transit time device. Avalanche breakdown effect is always reverse used in or observed in the reverse bias condition. So these devices are always connected in a reverse bias. Now see. Avalanche transit time devices are proper PN junction diodes with highly doped P and N regions. Many times in between P and N regions, there are intrinsic regions are also present that we are going to see after. Then they will produce a negative resistance at a micro frequency by using a carrier impact ionization, avalanche breakdown, and carrier drift in the high field intensity region under the reverse bias condition. From this we can say like that they will produce a negative resistance at a micro frequency by using impact ionization of a avalanche and a avalanche breakdown of the carriers, and that is in the reverse bias condition. There are three different avalanche transit time devices or ATD devices are impact diodes, Trapezoid diode and Barrett diode. We'll see when very short. The Sun impact diode structure, which is there is highly doped N plus region and P plus region. In between the highly doped N plus and P plus region, there will be the P region and the I region. So one will act as one terminal will act as a cathode and not proper PN junction is there. It is always connected in a reverse bias condition, and as the breakdown takes place, you can see the peak how the current is generated. Then impact ionization avalanche transit diode uh, is having some characteristics like the reverse bias voltage is greater than the breakdown voltage. Then and then only avalanche breakdown will take place. Then the high E field is applied across the junction. Then the holes acquires sufficient energy to tear the avalanche electrons of the atoms and bring them to the conduction band. How the avalanche breakdown takes place, everyone knows. Like if we given a sufficient reverse bias voltage to the device, then what happens? The electrons gets the energy from this reverse bias voltage and they will tear out the avalanche electrons, that is the outer electrons of the atoms, and from the avalanche band they will bring them to the conduction band. So if the large number of electrons are taken out from the avalanche band and sent to the conduction band, then suddenly the breakdowns of the bands will take place, a junction will take place, and the large amount of current will flow to the device. That is called as the avalanche breakdown. So here the same thing happens. Poles acquire sufficient energy to tear the valence electrons of the atoms and bring them to the conduction band. Then the onset of avalanche multiplication of electron and hole pair takes place. But the one drawback is that avalanche process creates a noise. It is nearly equal to 30 dB. So this device is quite noisy. Other than this, there is another one transit time device or avalanche transit time device, that is a Trapezoid diode. So Trapezoid diode is also called as trapped plasma avalanche triggered transit time diode. What it is called? Trapped plasma avalanche triggered transit diode. So this is another microwave energy device which is used as a both amplifier and oscillator. It was first reported by the Prager in 1967. That means before gun diode. It operates efficiently below 10 GHz and need greater voltage swing for its operation. It is a p-n junction diode characterized by formation of trapped space charge plasma within the junction region. So here, the within the junction, if you are connecting this diode in a reverse bias condition, then within a junction, a plasma is trapped, and this trapped plasma will make the device to operate in a negative resistance region within the junction region. Is typically represented by the current pulse and diode's depletion layer capacitance. Now if you see the structure of the device, it will have P plus region, N plus region and N region as shown in this diagram. Then typical silicon with the N-type depletion region having the width is 2.5 to 12.5 micron, P plus region 2.5 to 7.5 micrometers, and diode diameter range is 50 to 750 micrometers. This is the structure for this diode. The typical parameters are power generator is in between 1.2 kilowatt to kilowatt at an 1.2 gigahertz. The maximum efficiency is 75% at 0.6 gigahertz. Operating frequency range is in between 0.5 gigahertz to 50 gigahertz. You can see how the higher ranges of the frequencies it can operate with a small power. And it is very compact device also. Then it is having the applications like lower power Doppler radars. It can be used in the lower power Doppler radars, or it can be used in the local oscillators of the radar. It can be used in the instrument landing systems. It can be used in a radio altimeter. Radio altimeter radar is which is used to find out the distance of the ground or the distance of the plane above the ground. Above the ground layer, what is the distance of a plane? That can be founded by using a radio altimeter to find out. Basically, it is to find out the distance from the ground layer of an object. This radio altimeter is used, and it always requires that radio altimeter must be in a compact device. So to have this compact device, the compact generator is also used. That is in a Trapezoid diode. Then the last avalanche transit time diode is in a Barrett diode. Barrett diode is acronym of a Barrett diode is a barrier junction transit time diodes. It is a barrier junction transit time diode. It bears the numerous comparisons to the more generally used impact diode. It is as similar to an impact diode. This diode is used in the microwave signal generation like the more common impact diode, and also this diode is frequently used in the burglar alarm, where it can simply create a simple micro signal with a completely low noise levels. So wherever we want a tight security, where no one should enter, no burglar should enter, no external object should be there. So in that applications, the Barrett diode is used. This diode is very similar with respect to the impact diode, but the main difference between these two diodes is that Barrett diode utilizes the emission rather than the multiplication of avalanche electrons. If you see the structure of this diode, then P junction, P region, N region, then the drift region, or you can say that the drift in between the regions or junction is there. Then another P region is there. So uh, this diode or the current characteristics is also shown over here. Then we can write the difference in between the impact diode, trapette diode, and barrette diode. Many times this difference is asked. So at least 4 or 5 difference points you must remember. Given almost 10 difference points. Then the another one diode is a tunnel diode. All of you are aware of the tunnel diode. It creates a tunneling action from p-type region to the n-type region. As we give the signal, then the carriers from the p-type n-type region will tunnel to the p-type region. That all of you know. You can read also or from your books, or you can refer the notes for this. There is nothing to it. It is also operating same as it in a negative resistance region, so it can be used as an also